So molarity is moles of solute per liters of solution. And that's useful because that's going to get us into stoichiometry. You have a volume and you know how many moles of something are there. And that's what you always want to know in chemistry is the number of moles, because our stoichiometry is a mole-to-mole conversion. And so we saw that we can convert grams to moles of salt for solids to do stoichiometry, like chapter 9. In chapter 12, we learned how to convert volumes of gases into moles to do stoichiometry. And now in this class, we're going to learn how to take volumes of liquids and convert them into moles of solute to do stoichiometry, so that you can do stoichiometry with solids, liquids, and gases. This is a volumetric flask. Its purpose is to make solutions. You don't use these to measure things out. And so you'll add a mole of your compound. You fill it about halfway up with water. That just makes it easier to shake it up and dissolve it all. And once it's all dissolved, you fill the liquid up to the 1 liter mark. And now you have a 1 molar solution. You have 1 mole of potassium chloride dissolved in 1 liter of water. And so you have a 1 molar solution. So these volumetric flasks, their purpose is to make solutions. So calculate the molarity of a solution prepared by dissolving 9.35 grams of potassium chloride in enough water to prepare a 250 milliliter solution. We got to convert grams to moles. We find the molar mass of potassium chloride with our trusty periodic table. We add up the atomic masses of a potassium and a chlorine. And then we have our moles of potassium chloride divided by our liters, because molarity is moles per liter. And we get 0.502 molar potassium chloride. The molarity is signified by this big capital M, and it's read as molar. This is 0.502 molar potassium chloride. How many grams of potassium hydroxide are required to prepare 600 milliliters of a 0.450 molar potassium hydroxide solution? Well, we first we need to figure out how many moles of KOH do we need. So I need to make a 0.450 molar solution, that's moles per liter. And I'm going to make 0.6 liters of this. 600 milliliters is the same as 0.6 liters. Moles divided by liter times liter gives me moles. And so I calculate out that I need 0.270 moles of potassium hydroxide. Convert that back to mass, 15.1 grams. So now we can do stoichiometry. How many milliliters of a 0.175 molar mercury 2-nitrate solution are needed to precipitate 2.5 grams of potassium iodide? Here is our balanced equation. Let's double check it and make sure it's balanced. 1 mercury on the left, 1 mercury on the right. 2 nitrates on the left, 2 nitrates on the right. 2 potassium on the left, 2 potassium on the right. 2 iodides on the left, 2 iodides on the right. And so this is in fact balanced. So we got to convert our 2.5 grams of potassium iodide to moles. And now we do stoichiometry. I need 1 mole of mercury 2-nitrate to neutralize 2 moles of potassium iodide. So it's a 1-to-2 ratio. And then I convert to a liquid. They removed a step. You could say moles is moles per liter. So you could have 1 liter here and then do another step times 1,000 milliliters per liter. They just threw in 1,000 milliliters directly because that's the same thing as a liter, so they saved a step. But that's why they're doing that. And so this gives us how many milliliters of solution we need. In 43.0 milliliters of solution, we will have enough mercury 2-nitrate to precipitate out our 2.5 grams of potassium iodide. Any questions on that? Questions at all? How many grams of silver chloride will form by adding enough silver nitrate to react fully with 1,500 milliliters of a 0.4 molar barium chloride solution? Well, we're going to take our 0.4 or 1,500 milliliters times 0.4 moles per liter. Well, since this is 1,500 milliliters, they're just putting this in as 1,000 milliliters. 1 liter is the exact same thing as 1,000 milliliters. That's why they can use them interchangeably. In stoichiometry, we form 2 moles of silver chloride for every 1 mole of barium chloride consumed. Convert back to grams, 172 grams of silver chloride will form. Dilution. This is adding a pure solvent to a solution to make it less concentrated. Let's say I like super sweet Kool-Aid. I make a really concentrated amount of grape Kool-Aid. I have like 8 Kool-Aid packets and a pound of sugar, and I only made like 2 cups of it. So it is super concentrated, and you don't like this Kool-Aid because it's too much for you. You can take a little bit and add water to it and dilute it down to what you like. And the formula we use is the initial molarity times the initial volume equals the final molarity times the final volume. Why? Because molarity is moles per liter times volume is liters. And moles divided by liter times liters just equals moles. So in the end you get mole equals mole. And because you're only adding pure solvent, you're not changing the number of moles in there. And so if you add pure water to this Kool-Aid, the number of moles of Kool-Aid you started with are the same moles that you end with. There's just a lot more solvent, so it's a lot less concentrated. So what volume of a 12 molar hydrochloric acid solution is needed to make 500 milliliters of a 0.1 molar hydrochloric acid solution? Well, again, M1V1 equals M2V2. And we are solving for the initial volume. How much of a 12 molar solution is needed to make 500 milliliters of a 0.1 molar solution? So to solve for the initial volume, we divide each side by M1. Whatever you do to one side of an equation, you have to do to the other side. M1 divided by M1 is 1. Anything divided by itself is 1. And then we take our numbers, plug and chug, 4.2 milliliters. And so 4.2 milliliters, and then you slowly add that to water. You always add acid to water, never water to acid, because you want to dilute the acid. If you add water to acid, it can react and spatter, and you want to avoid that. So it's always important to slowly add acid into water so that it's always being diluted. Calculate the molarity of a sodium hydroxide solution prepared by mixing 100 milliliters of 0.2 molar sodium hydroxide with 150 milliliters of water. The important thing to remember here is they're both aqueous solutions, and so the volumes will be additive. When you have the same liquid, volumes are additive. And so your final volume will be 100 plus 150, that's 250. And again, we're solving for the final molarity, and our final volume will be 250 milliliters. So our initial molarity, the 0.2 molar, times the initial volume, 100 milliliters, divided by the final volume, 100 plus 150 is 250, gives us 0.08 molar sodium hydroxide. And again, whenever you're diluting something, you're just adding pure solvent, concentration is going to go down. Colligative properties. These are solution properties that depend only on the number of solute particles and do not depend at all on the nature of those particles. And the common properties are vapor pressure lowering, boiling point elevation, and freezing point depression.